Today we'll start the atomic structure and the periodic table. So in this topic we will discuss the structure of an atom, the mass spectrometer, the electronic configuration, how the electrons are arranged in an atom, shells, subshells, and later at the last part we'll discuss the trend in the melting point. So in the first part about the structure of an atom or atomic structure, we should know the subatomic particles. So what are the subatomic particles? So the subatomic particles are particles which are present in an atom, which are protons, neutrons, and electrons. Then their position, we have a nucleus. Around the nucleus, the particles are there, known as electrons, revolving around the nucleus. And inside the nucleus, we have subatomic particles such as neutrons and protons. So we find protons and neutrons inside the nucleus, where electrons are revolving around the nucleus. Then when we compare their relative mass and relative charge, so actual mass, like we have the mass of the proton. So mass of the proton is 1.6 into 10 to the power minus 27 kilogram. Mass of neutron is also 1.6 into 10 to the power minus 27 kilogram. And mass of electron, which is the lightest particle here, having a mass of 9.11 into 10 to the power minus 31 kilogram. These are the actual masses of proton, neutron, and electron. But when we take the simplest ratio, we divide by the value, each value by 1.6 into 10 to the power minus 27. So what we get? We get 1 here, we'll get 1, and here we'll get 1 divided by 1840. But they rounded off to 1800, but it is like 1840 or 1837, the actual value, but they rounded off to 1800. That's a relative mass or comparative mass. Because neutron and protons have the identical mass, that's why it is written 1 and 1. Electron is the lightest one, the ratio is 1 divided by 1800 or 1840. When we compare the relative charge, proton, which is positive, having a relative charge of 1.6 into 10 to the power minus 19 coulombs. Neutron is a neutral particle, does not have any charge, net charge, and electron is also having 1.6 into 10 to the power minus 19 coulombs. So when we divide by 1.6 into 10 to the power minus 19, this will come out as 1 or plus 1. The nature is positive. This will be 0 and this will be minus 1. So these are the relative charges of these protons, neutrons, and electrons. When we represent an atom, we represent the symbolic representation. We represent by mass number, or also called a nucleon number, which is a sum of neutron and proton. And there is atomic number, which is a number of proton, then the symbol of that element. So we simply represent element by symbol X, A, and Z, or it can be X, Z, or A. Sometime some of the periodic table you will find a proton number is written at the top, but it does not make difference, as you will the atomic mass number or nucleon number will be either equal to or greater than the proton number or atomic number. So atomic number is a number of the protons which are present inside the nucleus, and the mass number or nucleon number is a total number of protons and neutrons inside the atom. So if we need number of neutrons, we'll subtract the two, so we'll get the number of neutrons. So example, say we have beryllium, which is example 4 and 9. So what is A here? Atomic mass, A, or nucleon number basically, or the mass number. The higher number is a nucleon number, so nucleon number is 9. What is atomic number represented by Z? That's equal to 4. How many protons are there? Number of the protons, that is given by Z, so equal to 4. Number of neutrons, that is given by A minus Z, so that will be equal to 9 minus 4 equal to 5. And to get the number of electrons, because it's a neutral atom, does not have any net charge, so to be a neutral atom, the number of proton and number of electrons should be same. But if it's a negative charge, then electron number is higher, and if it is a positive charge, then proton number is higher. So in this case, because the neutral atom does not have any net charge, so the number of electron will be 4. Is it clear this part? How to work out the nucleon number, the atomic number, number of proton, neutron, and electrons? Then definition of isotope. How we define the term isotopes? Isotopes are the atoms with the same proton number but different neutron number. So example, if we have atoms with same proton number and different neutron number, like chlorine you can take. So chlorine, one of the isotope is 35 and 17, and another one is 37 and 17. So what is A here in the first isotope? A is equals to 35. What is Z here? Z is equals to 17. To get the number of protons, that is given by Z, so that is 17. To get the number of neutrons, it is A minus Z, so that will be equal to 35 minus 17 equal to 18. And to get the number of electron, that is also given by the same number as proton, because it's a neutral atom, so it will be 17. When we check the other atom, which is 37 and 17, so A is equals to 37, Z is equals to 17. To get the number of proton, that is given by Z, 17. To get the number of neutron, it is A minus Z, so it will be 37 minus 17, which is equals to 20. And to get the number of electron, because the neutral atoms are 17. So when you check, the two atoms have the same number of the protons, which is 17, 17, but they have different number of neutrons. So we call them as isotope. So atoms with the same number of protons and different number of neutrons are referred to isotope. And then relative isotopic mass, it's an average mass of the isotopes which is compared with a carbon-12. We call that as relative isotopic mass. So definition of relative isotopic mass is mass of one atom of an isotope compared with 1/12 mass of carbon-12, because relative mass is an average mass which is compared with carbon-12, but relative isotopic mass is a mass of the isotopes, mass of an isotope which is compared with carbon-12. So isotopes have the similar chemical properties. Why they have the similar chemical properties? Because they have same number of electron in the last shell. So as they have same number of electron in the last shell, the the chemical properties depends on the valence electrons. That's why they have the same chemical properties. Physical properties slightly vary because they have different masses. That's why they have different physical properties. Then the definition of relative atomic mass, average mass of one atom compared with 1/12 of one atom of carbon-12, and relative molecular mass is average mass of a molecule compared with the mass of one atom of carbon 12. So these definitions are important. What I highlighted, you have to learn these definitions about the relative isotopic mass, relative atomic mass, and relative molecular mass. Then how we can find these masses? So for that, we use a device which is called a mass spectrometer. So basically a mass spectrometer is a device which is used to find the number of the isotopes, the atomic masses, the molecular masses, and it is having four different stages. This is how the mass spectrometer, the top view of a mass spectrometer. Basically what we do, first we add a sample here, and that sample is vaporized. Vaporized means we convert into vapor or we convert into gaseous state. What is the purpose why we convert this sample into a gaseous state? Because fluids such as liquid and gases can flow. Example, if I have sodium, which is Na, sodium is solid at room temperature. So if I add sodium here, that sodium solid will not move. Why it will not move or it cannot flow? Because it is solid. Solid cannot flow by itself. Liquid and gases can flow. So first thing what we do, we vaporize the sample, or the vaporized sample is added so that it can flow. Then what happened? The four steps in the main steps are then ionization, and then deflection, acceleration, deviation, and detection are there. The other step, but the first step, the first step should be the sample must be vaporized sample so that it can move easily. Then after vaporized sample, the sample in a gaseous state, like example, I'm talking about sodium. So I have sodium in a solid state. So first I increase the temperature, so I will have a sodium in a gaseous state. So we have a sodium in a gaseous state. Then what we do, the second step, in terms of sequence, because the first step, it is obvious that it should be vaporized sample. That's why it is not mentioned that as a first step, because that's an obvious thing. Then the first step in terms of procedure is ionization. What happens in ionization? We knock out the electron from the atom. We call that as ionization. And how we do this? Like we have a example, we add a sodium atom here in a gaseous state. So we add sodium atom in a gaseous state. We target this sodium by a fast moving electron. So this fast moving electron will knock out the electron from the sodium atom, and what it will create a sodium positive ion, and it will have two electrons. Why two electrons? Because the electron we incident, and the other electron, the extra, because the one which we use for to target the sodium here, that is released, as well as the extra electron from the atom of sodium is released. That's why the total net will be two electrons released from this sodium. And how it is done? So the vaporized sample is injected at a low pressure. Then an electron guns fire the high energy electron. So this is the electron gun, and it will fire the high energy electrons. And these electrons knock out the outer electrons or electrons, and it will form a positive ion. Like example, in this example, say titanium is used. So titanium is there, turned into titanium ion by loss of electron. But this is not the complete equation. The complete equation should be like titanium be targeted by electron, and it will turn into titanium ion, positive ion, and it gives two electrons, the one which we use and the one which is released. Is it clear? The first step, the ionization. Then the second step is acceleration. How we accelerate? So basically now, as we are talking about, we in our example we took sodium. So first we ionize the sample, so sodium is converted to sodium ion, positive ion. So what we do, a negative electric field accelerate the positive ion, so we apply electric field here like a positive charge. So this, or example, because it's a positive charge, so we can apply a negative. So unlike charges attract each other, so this sodium ion is accelerated or speed up. So by using the electric field, a negative electric field, we accelerate the positive ion and make into a beam. How we make into a beam? Like in the first stage, it is producing lot of sodium ions. As we are using an electron gun to accelerate, but not all of the sodium ions are passing through this electric field. Only the sodium ions which are in the center, they are able to pass through in one line, so it will make a beam. The other particles are attracted towards the electrode and it is stopped by this electrode. So what we get as a result, we will get a beam of sodium ion which is coming out from the electric field. Is it clear, the second part, the acceleration? Then third, what we do, we apply a magnetic field. So the beam of a positive ion is deflected by a strong magnetic field. So we have a region here, like this gray region is representing a magnetic field region. So as this gray region is representing a magnetic field, so it will deflect. Example, if we have two isotopes of the sodium, one is 23 and 11, another one is 24 and 11. So what will happen? The two isotopes will take different paths. Why the two isotopes will take a different path? Because the deflection depends on mass to charge ratio. The one which is having a greater mass to charge ratio will have a small deflection, and the one which is having a smaller mass to charge ratio will have a greater deflection. So mass to charge ratio and deflection are basically inversely proportional. So what is the mass to charge ratio? Like example, we have two isotopes of the sodium, 11 and 23 with a charge 1 plus, and we have another 11 and 24 with a charge 1 plus. So what is the mass to charge ratio for this one? Mass is 23 and the charge is plus 1. So 23 divided by plus 1. So the mass to charge ratio is 23. What is the mass to charge ratio for the second one? The mass is 24 and the charge is plus 1. What we will get? We will get mass to charge ratio is 24. So which one deflect more? A mass to charge ratio 23 or 24? Which isotope will have a greater deflection? Isotope with a charge, mass to charge ratio 23 or 24? The mass to charge ratio and deflection are inversely proportional. Smaller mass to charge ratio, it will have greater deflection or deviation. So when we check, this is having a 23, so this will have a large deflection in a magnetic field, and the one which is 24 will have a small deflection. So what happens? Sodium which is 11 and 23 will deflect more, and the sodium which is 24 and 11 will deflect less. Then at the last part, what we have, is it clear, this part, the deflection? And then the last part is detection, like how we see them. So ions reaches a detector and generate a small current. So when it generates a small current, it shows the peak, like on the computer screen we see the peaks. On x-axis, we have the mass to charge. On y-axis, we have relative abundance or the percentage abundance. So example, the numbers are there. So this is 20, 22, 23, the mass to charge ratio 24, 25, and so on. And here the numbers are there like 50%, 100%. So what we see, if we are getting the two peaks, so the number of the peaks decide the number of isotopes. So if we are getting the two peaks, so what it shows we have two isotopes. And the number of the peaks here in a mass spectrum for an element representing the number of isotopes. When we have atom, like element in the atomic state, and we are getting two peaks, it means there are two isotopes. And the relative percentage on the y-axis, the one which is more will give a greater relative percentage, and the one which is less is giving a smaller relative percentage. So example, in this example, say this is 80%, so this one is 20%. So we are getting the two peaks. It shows that there are two isotopes and they have different relative percentage. Like one of the isotopes is higher than the other. Sometimes both isotopes are in the same ratio, so we'll have 50-50%. But sometimes we are getting one peak only. In a mass spectrum, the mass to charge ratio, if we are getting only one peak, so what we conclude, if we are getting only one peak, so we can say or conclude that it is having only one isotope. It does not have any other isotope. So sample is having one type of isotope. Is it clear? Like using a mass spectrometer, how we can work out the number of the isotope. So you can see we have, first we vaporize the sample, then we accelerate the sample, then we deflect the sample. So the path of a heavy, this will be the path of the heavy and this will be the path of the lighter. Lighter one deflect more, heavy one will deflect less. And keep one thing in mind, this is, we assume that the charge on the ion is +1, because sometimes what happened, when we are ionizing the sample, sometimes two electrons are being removed. Like you have sodium atom in a gaseous state, you target by the electron. So what is our assumption? Every time only one electron is removed from the gaseous state. But practically, it's what happens sometime when we target this sodium, example in this case sodium by an electron, sometimes two electrons are removed. So if two electrons are removed, we'll get a different mass to charge ratio. Like here sodium is 11 and 23, this is also sodium 11 and 23, but the mass to charge ratio for sodium, which is +1, 11 and 23, so mass is 23 and the charge is +1, so we'll get at 23. But when you check for sodium +2, mass is 23, charge is +2, so it will be 23 divided by +2, so we'll get at 11.5. So sometime it might happen that we are getting these peaks as well due to removal of two electrons, but we assume that only one electron is removed. So example, this is a relative atomic mass of, this is a mass spectrum, the result of a mass spectrum of magnesium. So where we are getting a peak, we are getting a peak at 24. we are getting a peak at 25, and we are getting a peak at 26. And what is our assumption here? All the cases we assume that only one electron is being removed. Then the percentage of each isotope, the percentage of 24, magnesium 24 is 78.7, 25 is 10.13, and 26 is 11.7. How we can find the relative atomic mass by using the isotopes? The formula to calculate the relative atomic mass, the percentage of isotope multiplied by its abundance. Percentage abundance multiplied by its mass. So what is the mass? First, it is 24, so we write 24. And what is the percentage? 78.7, so 78.7. What about the second one? It is 25, and the percentage is 10.13. And the third one, 26, divided by percentage is 11.17. And then that total is divided by 100, because the total percentage is 100. So we'll get as 24.3. So 24.3 gram per mole is the relative atomic mass of this magnesium sample. Is it clear how we can work out? Using the percentage abundance, how we can work out percentage abundance and mass to charge, how we can work out the relative atomic mass. Sometime, instead of giving the percentage, there is no label on this. So sometimes the percentage is not given to you. Then how you will do these type of question in which we don't have percentage? So you can divide this into units. Like example, if I say this is 2 units, you can label 2 units, 4, 6, and 8. So how we do this one? The first one is 24 multiply by what? How many units are there? It is between like 6 and 8. I'm assuming it is between 6 and 8, so it is 7 plus 25 is approximately 1 unit plus 26 is approximately 1 unit. Then that divided by the sum of the units. So what are the sum of the unit? This was 7 unit, this is 1, and this is 1. So total sum will be 9. So 25 into 7. Basically, we are taking the ratio here. Plus 25 into 1 plus 26 into 1 divided by 9. So we will also get the relative atomic mass. So if in the question the percentage abundance is not given, you can use this technique as well. Or what else you can use? You can also use the measurements. You can use a ruler here. You can use your scale and you can measure these heights to work out the relative atomic mass. So example, when you measure the height, so this was 8 centimeter example. You measure the height, so this was 1.8 centimeter and this was 1.7 centimeter or 1.9 centimeter. Then how you will get the answer? So this will be 8. Using a ruler scale, you measure the height multiplied by 24 plus 25 multiplied by 1.8 plus 26 multiplied by 1.9 and then divided by the sum. So this will be 8 plus 1.8, so it will be 9.8, and then 10.8 plus 0.9, so it will be 11.7. So this will be divided by 11.7. So you will also get the relative atomic mass. Is it clear how we can work out the relative atomic mass if the percentage is not given to us? Then sometime you have molecules such as chlorine and bromine. So if you have a molecule such as chlorine and bromine, so you will get different peaks for the molecule. How you are getting a different peaks for the molecule? Example, as we know, for a chlorine, Cl2, chlorine is a molecule, but there are two isotopes of the chlorine which exist. One is 35, another one is chlorine 37. And the chlorine 35 is 75% and chlorine 37 is 25%. So what will be the mass spectrum of Cl2? So mass spectrum of Cl2, how you work out, because you have Cl2. So what is the possibility that in Cl2 maybe the two chlorine which are present, both of them are 35. So if both of them are 35, so where you will get a peak, 35 plus 35 you will get a peak at 70. Maybe the two chlorine which are present, one of them is 35 and the other one is 37. So where you will get a peak? You will get a peak at 72. And maybe both of the chlorine which are present are 37. So where you will get a peak? You will get a peak at 74. That's why you are getting a three peaks for chlorine. Maybe at 70 is due to both 35. At 72 is one of 35 and 37, and both are 37 at 74. And why the 35 one is higher than other one? Because the percentage of 35 is higher. That's why when two 35 are joined together, you will get a higher percentage as compared to 35-37 or 37-37. Is it clear? For a chlorine molecule, we are getting three peaks because it is having two isotopes. Same way for bromine. For bromine, there are two isotopes. One is 79, another one is 81. So if we are talking about bromine molecule, so what are the possibility? Because we know in bromine molecule, maybe both of them are 79, maybe one is 79, another one is 81, and maybe both of them are 81. So if both of them are 79, we'll get a peak at 158 because 79 plus 79. One is 79, one is 81, so we'll get a peak at 160. And both are 81, so we'll get a peak at 162. And which one will be the highest one? Because these two bromine are 50-50%. But when they join together, because it is 79-81 or 81-79, so the highest peak will be for 160. And 158 and 162 will be of same proportion because we have both as 50%. Is it clear? So why we are getting three peaks for bromine and three peaks for chlorine? So what are the uses of the mass spectrometer? A mass spectrometer have been included for space probes to identify the element, because using a mass spectrometer we can work out the element. It is used during the testing in a sport to identify the chemical present in the blood. It is also used for quality control in pharmaceutical to identify the molecule from the sample. And it is also used for radioactive dating for determining the ages of the fossil or human remains. Like identifying the amount of sample present, we can work out what is the age of this fossil. So today we discussed the mass spectrometer. Any question related to this topic? Tomorrow we'll do questions related to mass spectrometer. So you will have a better understanding of the topic. Any question related to the class today? So I'll end the session and share this.